Hello, everyone. Thanks for joining. Today, I would love to share with you some secrets on how to save millions of dollars when running workloads on your infrastructure, for example, in clouds. That secret knowledge is not always comfortable to know and follow, as it requires some discipline, good tools, and some effort. It might help you a lot, but it might also irritate you or annoy you. And that's a good thing, right? This is because my talk is an oyster talk. And it's not like I love seafood. I mean, I love, but that's unrelated. It's the fact that oyster has these special characteristics. When you damage or irritate oyster, two things can happen. Either it dies or a beautiful, amazing pearl grows in it. You see, within 20 minutes, I cannot teach you in all details how to optimize to save that money. What I can do, I can give you general advice and directions that ideally also irritates you. So amazing pearl, so effect might grow out of it. And finger cross, you will not die. Make sense? Let's go. Before we start, let's start with some short introduction. My name is Bartek, Bartłomiej Płotka, but you can call me Bartek. I am a principal software engineer at Red Hat, and I love open source, Go, distributed systems and observability. I maintain a lot of projects in open source, including Thanos and Prometheus, two monitoring systems in the CNCF, so Cloud Native Computing Foundation landscape. I do a lot of mentorships and I mentor a lot. I recommend joining our initiatives as well. And I'm CNCF ambassador and the technical advisory group tag observability tech lead in the CNCF. I also wrote a book, and it's called Efficient Go. And the book explained all the things I mentioned in the talk. I will be mentioning in this talk in very details using my favorite programming language, Golang, as an example. However, as it turned out, accidentally, actually, majority of chapters are language agnostics, and they can apply to any software really. So let me start with the quick story. Every good presentation has to have a story, right? And in this story, I would love to show you a main pitfall I see nowadays in DevOps SRE software development worlds. This happened a few years ago in the open source project in the CNCF landscape I lead, Thanos. Thanos is essentially a scalable monitoring system which implements a bunch of microservices in Go to store your metrics cheaply and effectively. One of the microservices is called Compactor, and it's a key component in Thanos system. For the purpose of this talk, it does not matter what it does. It essentially talks to object storage and processes some data. The point is that it's very critical in the system, and it can process gigabytes, if not terabytes of data every day. At the very beginning of Thanos project, common thing happened. Right? The first iteration of the project was very successful. Many companies and users jumped on it, deployed, installed, used it. And with as almost every early implementations, compactor code was a bit naive and inefficient. It did the work, but it was consuming a lot of memory, lots of gigabytes, and often caused problems for the users. And we have lots of issues around that, and we can see even from reports that the memory usage was skyrocketing, causing out-of-memory exceptions on the machine or the process. So inevitably, something had to be done in the project, and community and the team gathered around, and we were looking for solutions. However, many of suggestions that were proposed by the community, by the users, were very interesting. And we started to see some patterns on how engineers prefer to solve those problems. So let's go through the proposed solutions. First of all, some community members were asking for the right configuration that works. I don't know where it comes from, perhaps from some software like Java JVM that has lots of performance flags that has to be tuned, but it's not a good design, I would say. It's not like every software has a magic, flags that tune performance. If there is inefficient code, there is inefficient code, and usually no configuration can change it. At the end, this solution was not great for Thanos. Thanos doesn't have such flags. Another common solution is to ignore a problem, right? We can just add more resources to the cluster. We can add bigger nodes with bigger machines with more memory. Of course, this has limitations, right? First of all, it cannot scale unlimitedly. There's limit to machine types we have in the clusters, and they get expensive at some point. And we overpay, right? We run inefficient software and just keep putting resources for it. We overpay for that computations. Third recommendation from the community was to scale out horizontally. To do this, we would need to shard the work into smaller pieces and schedule that on multiple processes, so multiple machines. We can then use smaller machines, but more of them. And while it solves some problems, it's still, we are adding a huge complexity of distributed system on top of a problem that might be solved differently, right? And we are still overpaying, right? Because we are running inefficient software just in chunks, and we still overpay, but just with different instance types. Plus, we pay for additional overhead of this distributed system. So generally, it's not always worth it. Finally, some people say, wait, why we invest in Thanos project if it has so inefficient compaction? Let's switch to other open source system or cloud vendor that can store time series and solve our goals. Well, sometimes that might be a good solution, but because there are some, design limitations, license problems, community problems, so jumping through different projects might be necessary. However, there are problems as well. There are costs. Huge engineering costs to learn a new tool, operational model, research benchmarks, and really to migrate all your data. And what if other software is also inefficient, maybe in other aspects than Thanos? And maybe, somewhere Thanos is more efficient in some aspects. Because, every software has some weaknesses, and just jumping through projects is not always a good idea. So with all those suggestions, it turned out that the simplest solution was to actually optimize the code optimize the software on the code and algorithm levels. With some work from the contributor from Cloudflare, we optimized Compactor to use, algorithm that streams essentially, so process data in place, which was all the Thanos needed. It solved the memory problem. 4 years later, today, and Thanos Compactor still did not need to be scaled up or scaled out or be replaced by other solution. It just works, right? For majority of Thanos users on our big setups. What's crazy is that we were so close to accept significant complexity, pain, and cost for everybody, if not that, kind of simple code optimization. So there are two lessons to be aware here. First of all, software efficiency on the code level and algorithm matters, and is usually more achievable than you think. And second is that there is a common pitfall these days called closed box thinking, and more on that later. But there are many reasons why we overpay and waste money in clouds. But I believe closed box thinking and lack of pragmatic process and skills for software efficiency optimizations are important factors. It might be because of many patterns emerge, like DevOps, SRE, high-level programming languages, or even no-code frameworks that made engineers a bit lazy on making our code faster or more efficient. That's why I would argue we entered the era where premature scalability and premature project jumping is much bigger threat these days than, let's say, premature optimizations, code optimizations. So how to solve this? I would love to share with you 4 things that, in my opinion, are most important in software optimization journey. First of all, be aware of optimization levels. Optimization level is essentially a level on which we can apply optimizations. So first of all, we have a system level, right? So essentially, the system level optimizations were proposed in our story, like tune the configuration, horizontally scale out the system, pay for cloud vendors, switch to different system, and my favorite one, which is let's rewrite the whole thing in Rust or Carbon, which is a new language for efficient programming, that works well with C++. But that's not all the levels we have. We have also algorithm and data structure, which usually focus on to improve asymptotic complexity. So the growth factor for the runtime and space cost based on the input. For example, switching from one sorting algorithm to another might improve efficiency of our solution. whereas improving on code level or compilation level can yield improvements in constants of this asymptotic complexity, so the real complexity of our solution. For example, making sure our code allocates some bytes on stack versus on heap can improve efficiency on the code level. Finally, you can optimize on operating system or hardware levels. So you could switch to different ones or configure them better, and it as an overall solution will be more efficient as well. So what's the closed box thinking in this? Well, it is when we are biased to solutions that allow us to not dig too much into software. It treats software as a closed box, right? That you don't want to open, you don't want to see what's inside, and even worse, to change it. Again, it can have many reasons. Perhaps the organization has more engineers who are not experienced in programming or optimizations or technology that this certain code is written in. And sometimes closed box thinking makes sense as well, right? If we absolutely can change the code. However, I feel we often scope code changes to not get out of our comfort zones. And that's not great because almost no software is efficient, fully efficient these days, unless we are talking about grep, which has like 50 years already. So if you take any solution out of the shelf, you can expect to optimize resource usage at least 10 times for the functionality you care for. So we are missing a lot by avoiding touching code and algorithm level of our solutions. But of course, there's also another extreme, right? I call it my baby thinking. It's a common in maybe competitive programmers and less experienced developers, which are biased toward changing their code, where simpler solutions like system level or operating system optimizations are more appropriate. This also happens when engineers are missing a big picture, or they don't know where the real goal is. So there are both extremes in the spectrum. So what I would suggest here is to escape both closed box and my baby thinking and enter open box thinking. My recommendation is to be aware of all those 6 optimization levels and roughly understand what is the cost of each, depending on your organization, knowledge, skill set, and passion. However, I would not scope algorithm and implementation optimization levels so quickly, especially when the code is in open source and generally accessible language, written in this language, for example, like Go, Java, Python. With the right mindset and tools, we can optimize a lot on those levels, more than we think usually. So what is this mindset I'm talking about? In my experience, I was always relying on a certain flow for optimizations. But I truly realized that the kind of like pattern of this flow only when I was writing my book. I call it TFBO. TFBO means test, fix, benchmark, and optimize. And it essentially is an extension to the TDD, so test-driven development, that focuses on creating software that meets both functional and efficiency requirements. For those not familiar with TDD, it's an amazing software development practice where you write your functional test before you change your code. It's amazing on many levels. I love it personally. It ensures your testing is reliable, your work has clear expectations, is pragmatic and well tested. I wrote about this in my book in detail, but my suggestion here is to do the same for efficiency after your code is functionally complete. I call this BDO, so benchmark-driven optimization. You first create a benchmark, use it, and only then you optimize your code, right? Only if it's needed. You have to have the data about efficiency of your software before you even start optimizing. So if you combine TDD and BDO together, we have a TFBO flow. And it goes like this. We first test our software, we fix if needed. Then if all test passes, we start benchmarking. Then if we are happy with results of those benchmarks, we just release. No optimization is needed. However, if we are not matching our expectations, we look for the main bottleneck. So the system component or piece of code that contributes to the problem the most. For example, code line that allocates the most, the highest number of memory. Because there's no point in optimizing piece of code which is rarely used. And finally, once we have this bottleneck, we can try to find optimization. And we should look on any optimization level. Perhaps code is not the best level. Perhaps, we should change algorithm, maybe, system. So be aware of those things. Finally, we repeat the process. And we always start the loop with functional tests because we don't want to waste time optimizing code that is yielding wrong results, right? Finally, once functional tests are passed on our optimized code, we benchmark it and compare with the baseline, with the past results, and then based on that, we know if it's better or not, and then if it's matching our requirements. And this is what I've seen used by experts, and that's why what I used myself, and I think it's kind of clear. Another extremely important suggestion from my side is to set clear efficiency requirements, which I call in my book RARE. I read this acronym as RARE because it's very rare to have them, really. And socially, otherwise it's hard to pronounce that. So the problem is that when we follow TFBO, so test, fix, benchmark, optimize, flow, or any other optimization process, at some point we have to stop optimizing, right? Or know when to start optimizing. We don't do that just for fun. We are paid to solve certain problems. Now, this is not trivial. How we decide about that? When your solution is fast or efficient enough? Typically, we don't have that information, which is pretty bad, because at this point, every optimization is premature. Sometimes when we ask for clear efficiency requirements from someone, or we define ones, we have some fuzzy requirements. For example, your code is slow, or it has to use less memory. This is not really much better, as we still don't know if our code that used to allocate, let's say, 20 gigabytes of RAM, and then we optimize it so it allocates 5 gigabytes less. Is it now okay, or should we optimize further? Where's that exact decision? That's where RARE comes in. We have to ask or define clear goals. So ideally, resource-aware efficiency requirements. And I mean literally a average number on paper for latency and resource consumption like memory. It's kind of funny, right? Like every software engineer have to do it on a system design interview, those kind of calculations. But honestly, we do that very rarely in our work, and at least in my experience, and that's pretty sad. One of the reasons why we have to be very clear about those goals is that many optimizations has to be accepted deliberately. They might sacrifice latency for lower memory usage. Or opposite, when cache is introduced, for example, we use more memory but improve latency enormously. Without clear goals, we can't make that decision. And here is the irritating part potentially. I think lack of clear goals or procrastination to define ones, because it's uncomfortable, right? Like it's like setting condition to failure, for failure. Those things are main reasons why we overspend on infrastructure these days. That's why I would propose to set RARE, resource-aware efficiency requirements, ideally on paper, with stakeholder signature. Don't worry if you can't match those expectations or like requirements later on. Everything is negotiable, everything has its cost, but we have to have those numbers. Last but not least, we need observability in our journey. The TFBO flow requires observability mainly in two parts. When we try to assess efficiency of our software and when we are trying to find the bottleneck. You can use really any observability signal for that, metric, logging, tracing, continuous profiling, but my TLDR recommendation and preference is following. Use metrics in micro and macro benchmarks to assess how fast or how much resource hungry your solution is. Use profiling or continuous profiling for those benchmarks to find out main bottlenecks very quickly. I also mentioned on the slide a few fully free to use open source solutions that we use on production, and yeah, they are super, super nice. I recommend to check them out. To sum up, the main takeaway is that software efficiency optimizations are very important and accessible to everyone. And we talked about 4 things that make those easier. Awareness of all optimization levels, clear goals in a RARE style, follow pragmatic flows like TFBO, so test, fix, benchmark, optimize. It tells you what's next and allows you to not get lost. Finally, invest in observability tools. You don't need to have all the tools and all the systems, but to me, metrics and profiling are must-have. So that's all for this talk. I hope you enjoy it. Hopefully I irritated you a bit as well. So like oysters, some amazing pearls will grow out of it. And yeah, thanks for joining me, and feel free to follow me or reach me on Twitter if you have any questions, feedback, or ideas. And yeah, the content we talked about today is explained in much greater details with code and observability examples in my books. So if you are interested, check that out as well. Thank you.